Thank you to Incogni for supporting PBS. We've spent the last decade listening to the vanishingly faint vibrations in the fabric of spacetime from black holes colliding across the universe. Now, hundreds of detections later, we finally thought we understood the story they were telling. But then we spotted something that should be impossible, a black hole smaller than known stellar astrophysics allows, a black hole that may have formed in the Big Bang itself. It may tell us something incredible about our universe, but also, equally importantly, about what this young field of gravitational wave astronomy has become. Before we get started, a couple of quick announcements. First, we have some new data. Liking and commenting really does help get the episodes shared. So, please do both of those things. And we've also learned that the number one reason that people support us on Patreon isn't actually the perks. It's simply to support the Spacetime community and the work that we do. So for those of you who do support, thank you so much. But don't get me wrong, there are perks and they're good. There's a link in the description if you'd like to join. This really would be a huge help. This month marks an incredible milestone. 50 years since humanity first landed on Mars. On the 20th of July 1976, Viking 1 became the first spacecraft to successfully touch down. To celebrate, we've created a limited edition 50 Years on Mars collection featuring the iconic Viking 1 lander as a UV glow t-shirt and hoodie. We also have a new desktop and gaming mat that shows the actual location of every Mars lander. If Mars exploration has inspired you as much as it's inspired us, check it out at the Spacetime merch store. Now, onto the episode. 10 years ago, LIGO detected gravitational waves for the first time. It was one of those discoveries that immediately felt like the beginning of something much bigger. Yes, we'd proved Einstein right, again, but we'd also gained an entirely new way of observing the universe. What else would that lead to? New types of collapsed object, dancing cosmic strings, echoes from the Big Bang, even cracks in the deeper depths of Einstein's theory. Revolutionary observations are exciting because we don't know what the new field might evolve into. Now, fast forward 10 years, we're finally far enough away from that first detection to ask what gravitational wave astronomy actually has become. Has it lived up to those expectations? Has it changed astrophysics? Or has it mostly confirmed what we already thought we knew? That question has been on my mind because LIGO, Virgo and Cagra released their latest gravitational wave catalogue. Now nearly 400 detections of gravitational monsters colliding across the cosmos. But just as we started to think we understood what we were seeing, building and refining our theories of how they must have come to be, something new appeared. Now, it's only a candidate for now, but if it survives further analysis, it may contain a black hole that's lighter than anyone thought possible. A black hole that could not have formed from a star. It's not confirmed, but people are paying attention, and we'll come back to it. Now, the first gravitational wave detection was a huge headline, and shortly thereafter, a Nobel Prize. Fair enough. The Laser Interferometer Gravitational Wave Observatory and its cousins are, after all, miracles of human ingenuity and chutzpah. The kilometre-scale vacuum systems, the mirrors isolated from vibrations smaller than the width of an atomic nucleus, sensitivity improving one observing run at a time until esoteric tricks of quantum optics pushed the fundamental limits of measurement. Thousands of scientists and engineers working together for decades to measure distortions of spacetime of only about 1 part in 10 to the power of 21. Virgo and then Cagra joined the two LIGO detectors to improve our ability to localize sources on the sky. An ecosystem of fast response traditional observatories made ready to follow up gravitational wave hits. So much work by so many people, even before the first detection of black holes colliding 1 billion light years away. But then something more interesting happened. LIGO and its partners got to work. We've since watched spacetime wobbles many hundreds of times and have now confirmed nearly 400 mergers of black holes with a few neutron stars in the mix. We quietly built something far more powerful than any one measurement of black hole mergers. We built a catalogue.
And in that catalogue lies a pattern, and in that pattern we can infer a universe. An interesting thing about every successful observatory is that it eventually fades away. And I mean that nobody asks anymore whether, say, the James Webb Space Telescope can see distant galaxies. We shifted to wondering at the galaxies themselves and then wondering what they tell us about the structure formation in our universe. We marveled that the Large Hadron Collider could make Higgs bosons, but then we dug into measuring the particle's properties and we asked what its existence tells us about the quantum structure of reality. The instrument disappears and the universe takes center stage. The same thing has happened with gravitational wave astronomy. Signals that once would have been buried in the noise have become routine detections. And the catalogue of mergers grew 10, 50, 100. Eventually, there were too many to think about one at a time. And I think that this is the moment that the field really crossed a threshold. The discoveries were no longer individual events. The discovery was a population of events. And it's in this catalogue that the real science happens. Now, there's actually a name for the transition that gravitational wave astronomy is going through. The philosopher of science, Thomas Kuhn, argued that scientific revolutions eventually settle into what he called normal science. It's a slightly unfortunate name because the most exciting science happens in this normal phase. In the case of a revolutionary observational technique, Kuhnian normality is the moment that a new instrument becomes dependable enough that scientists stop asking whether it works and start using it to answer questions that they couldn't even ask before. That's where gravitational wave astronomy is today. With a single detection, we can say that gravitational waves are real and that black holes sometimes merge, and we can measure things about the masses and the spins and the distances and whatnot. But with a catalogue of detections, we can infer a huge hidden population of black hole pairs out there that spend billions of years orbiting one another in complete darkness. And from the space-time ripples that wobble through the Earth from the last fraction of a second of their in-spiral, we can learn the properties of that whole hidden population. We learn that many of these black holes are much heavier than we thought likely. That taught us that there are unexpected growth mechanisms after black holes' initial formation for the collapse of massive stellar cores. From the black hole spins, we infer some really surprising things about the way these merging black holes find each other. A little while ago, when we were talking about the dark energy survey, I said that reality often hides in the relationships between data. That's what's happening here. The universe isn't revealing itself one merger at a time, it's revealing itself through the patterns those mergers form together. The inference chain is pretty incredible if you think about it. Remember that LIGO and co. never measure any of the stuff that we figure out. No ancient binary progenitor stars, for example. Not even the binary black holes themselves. We measure a minuscule ripple in spacetime lasting a fraction of a second. We get to binary black holes by asking what sort of phenomenon could have produced this. And once we build a catalogue, once we know the population properties, we can ask a different question. What sort of universe could have given rise to such a population? The ripple remembers the merger, and the merger remembers the parent stars, and with many ripples we can infer all the way back to the universe that produced the stars that produced the merging black holes and the faint signal that LIGO catches. All of astronomy really works this way. It's a particularly awesome example of reverse inference, where we're only given the after-the-fact traces and need to infer the processes that led to them, like a detective figuring out a crime from a room full of subtle clues. And astronomy is especially dependent on reverse inference because there's no rerunning the experiment. Other fields have the luxury of regrowing the culture in the petri dish or resmashing protons in the collider. Astronomy gets a handful of ancient photons, neutrinos, gravitational waves, and has to figure out the universe that created them. But before we can do that, we need this intermediate step of the catalogue, of the population, of what our universe normally makes. The work then of normal science is to understand what is normal. So maybe it's a good name after all. And the reason we care so much about the ordinary is that it allows us to prove ourselves wrong. attempting to falsify our models to disprove our ideas about the universe is the highest priority of science. And so a hallmark of a mature field of science is that it's no longer trying to construct the basic explanations, it's trying to break them. Instead of asking, can I explain this? A mature science asks, does my explanation still survive the next observation? Let's take the example of the correlations between the spins of merging black holes. If we assume that all merging black holes come from massive binary stars that formed from the same cloud of interstellar dust, then we have a prediction. The spins of those black holes should both carry the signature of the original rotation of the birth cloud. The binary black holes should have correlated spin. But when we look at hundreds of black hole mergers, we find that indeed many do have correlated spin, indicating formation by the expected process. But there is a second population in which the spins of the merging pair are uncorrelated with each other, pointing in random directions. That falsifies the hypothesis that all mergers come from binary stars. We now have to include a second population of black hole pairs that probably came together after their progenitor stars died. In that case, they probably found each other after falling towards the centers of dense star clusters. No individual merger points confidently to one formation scenario or the other, but every detection nudges the weight of evidence in a different direction. After hundreds of events, we start to be more confident that across the universe and back through its history, both of these processes played out, and that we live in a universe in which both are possible. The growing catalogue also hints that many black holes are a bit too massive and spinning a bit too rapidly and with spins a bit too aligned for either of those scenarios, allowing us to motivate another formation scenario. Some black holes probably sink into the dense gas disks surrounding active supermassive black holes in galaxy centers. There, the gas can shepherd them together, allowing repeated mergers that naturally produce unusually massive, rapidly rotating black holes. This is still just a hypothesis, but it's one that's increasingly consistent with the growing population of LIGO detections. But again, the evidence is only in the population, not in any one observation. This is why gravitational wave astronomy is rapidly evolving into a mature science. The individual discoveries are less important than the broader statistical picture. The universe leaves its most telling traces of its past in statistics, not in objects. A mature science interrogates those statistics to interrogate the models of the universe that might explain them, and to eliminate the models that fail to do so. A mature science is in the business of eliminating explanations until gradually the picture that remains looks like the universe that we actually live in. Which brings us back to that one curious signal of the impossibly light black hole. We don't directly measure the masses of each black hole. Instead, we measure a particular combination of the two masses, the chirp mass. So, on November the 12th last year, both LIGO detectors and Virgo quivered under an exceptionally faint spacetime ripple that suggested an extraordinarily low chirp mass. If confirmed, it's very likely that at least one of these objects has less than the mass of the Sun. Such objects should be impossible by the established models of black hole formation. A dead stellar core of less than 1 times the mass of the Sun collapses, but it doesn't collapse into a black hole. It forms a white dwarf. But above the Chandrasekhar mass of 1.4 solar masses, it becomes a neutron star, and only above 3 or so times the Sun's mass can a dead stellar core collapse into a black hole. Now, white dwarfs just aren't compact enough to produce a LIGO signal on merger, but neutron stars and black holes simply can't form at such a low mass, at least not via stellar evolution. But why did the field have to be mature in order to spot this thing? Well, imagine the very first LIGO signal had indicated a sub-solar mass black hole merger. What would we have concluded? Well, probably that our instrument or our analysis method was flawed. We would have spent months or years tweaking and recalibrating and hoping to catch another. Instead, this apparently tiny black hole merger came a decade in when we knew that LIGO reliably finds and measures appropriately large masses for its black hole mergers. We know the instrument and the analysis work. So now, rather than stressing that we messed up, we get to move forward with the science. LIGO has told us what is ordinary, and black hole pairs of 3 to 50 solar masses are routine. Those are consistent with black holes formed in the collapse of the dead cores of massive stars, but a subsolar mass black hole is not consistent with this picture. If confirmed, it will falsify the hypothesis that all merging black holes come from stars. We need yet another formation channel. If this thing is real, then the best explanation seems to be that those black holes are primordial, that they formed in the unimaginably dense conditions of the early universe before the first stars had begun to shine. Finding primordial black holes with LIGO would allow us to extend our reverse inference process all the way back to the moments after the Big Bang, and that's an extraordinary possibility, and so also requires extraordinary evidence. More detailed analysis is needed to ensure that this isn't a fluke of detector noise and that the inferred masses are correct. This candidate may still disappear or never rise to the level of a confident detection. That sounds disappointing, but it does mean that the process of this now mature science is working. Of course, if the subsolar masses prove to be real, then we have another mini scientific revolution. It starts with one detection, the first primordial black hole, then we find another, and build the catalogue and measure the population. From things like the number density and the mass distribution, we learn how and when these PBHs formed, just as we did with the regular black hole mergers. In the case of PBHs, we'd learn whether these things can explain dark matter and derive powerful constraints on the conditions of the extremely early universe. Finding multiple primordial black holes with LIGO would allow us to extend our reverse inference process all the way back to the moments after the Big Bang, and PBH detection would become normal science. Gravitational-wave astronomy is right now transitioning into a mature field, at least with respect to normal black hole mergers. Be excited when it uncovers extraordinary new things like the possible primordial black hole, but be satisfied when it doesn't, because this meticulous mapping of the normal is the real work and the key to an iteratively better understanding of the whole of spacetime.
Thank you to Incogni for supporting PBS. Incogni believes in the value of keeping our personal information private in a world where scams and identity theft often begin with your personal data being exposed. There are hundreds of commercial databases and data brokers who aggregate your personal information, including your name, address, and online activity, which is why Incogni was created. To track down and removes your personal data from multiple sites, including online directories, people search sites, and even commercial databases. Incogni also automates the removal process for hundreds of known data brokers who collect and sell your data without your consent. And with their custom removal feature, you can enter any additional info you want removed. To learn more about Incogni, just check out incogni.com/spacetime and use the code spacetime for 60% off Incogni annual plans.